Hello, this is Mrs. Decker, and this lesson is on Objective 2C, Theoretical Yield, and 2D, Percent Yield. Before we get started on the new lesson, we want to go back and review 2B on finding the limiting reactant. So go ahead and pause this video, and when you are finished with the problem, come back for the answer. Alright, so we want to start with our 23.8 grams of H3PO4, and we're going to convert that to moles of K3PO4 since that's what the question is asking us for. So we're going to use the molar mass, which is 97.93 grams in 1 mole of H3PO4. And then we'll use the mole ratio from the equation to go to moles of K3PO4. So we have 1 mole of H3PO4 in 1 mole of K3PO4. So when you calculate that, you get 0.243 moles of K3PO4. Now our second calculation is going from 52.6 grams of KOH to moles of K3PO4. So the molar mass of KOH is 56.09 grams in 1 mole. And then in the equation we have 3 moles of KOH to every 1 mole of K3PO4. So when you calculate that, you get 0.313 moles of K3PO4. So remember, the limiting reactant is the reactant that produces the lesser amount of product. So that would be H3PO4. The excess reactant is KOH. And the moles of K3PO4 produced is 0.243 moles of K3PO4. Okay, so before we get started with the calculations, we have to talk about the different kinds of yields. First is the theoretical yield, and this is calculated from the stoichiometry information. I will show you how to do that in just a few minutes. The actual yield is the mass of product that is actually obtained when the lab is carried out, and then the percent yield is a calculation to find out how accurate your experiment was. So to calculate that, you will do the actual yield divided by the theoretical yield times 100. Now, you will not be given this equation, so you need to know how to do it. An easy way to remember it is A over T. A comes before T in the alphabet, so A over T, actual over theoretical, and then times 100. Okay, so this is example 1 for finding the theoretical yield. Our example says if 4.5 grams of HCl are reacted with 15 grams of CaCO3, according to the following balanced chemical equation, calculate the theoretical yield of CO2. So step 1 is what we did in 2B. Find the limiting reactant and the moles of CO2 produced. So you're going to start with your 4.5 grams of HCl, and we want to go to CO2, and then we're going to do our second calculation from 15 grams of CaCO3, also to moles of CO2. So first step is to use the molar mass of HCl, which is 36.45 grams in 1 mole. And now go from moles of HCl to moles of CO2 using the coefficients from the equation. So it's 2 moles of HCl to 1 mole of CO2. So when you calculate that, you get 0.0617 moles of CO2. Second calculation is 15 grams of CaCO3, and use the molar mass to go to moles of CaCO3, which is 100.06 grams in 1 mole. And then the mole ratio from the equation, which is 1 mole of CaCO3 to 1 mole of CO2. So when you calculate that, you get 0.150 moles of CO2. So based off the answers that we've gotten, our limiting reactant is hydrochloric acid, HCl, because it produced the lesser amount of product. So the moles of CO2 produced is 0.0617 moles. Now step 2 is to take the moles of CO2 produced and convert that to grams of CO2. So 0.0617 moles of CO2. And we're going to use the molar mass to convert that to moles of CO2. So 1 mole of CO2 is equal to 43.99 grams of CO2. So when you calculate that, your answer is 2.71 grams of CO2. So that is our theoretical yield. If we start off with 4.5 grams of HCl and 15 grams of CaCO3, we should be able to produce 2.71 grams of CO2. Now, we determined that HCl is our limiting reactant and CaCO3 is our excess reactant. So now step 3 wants us to calculate how much excess reactant is left over. So to do that, you need to use the moles of CO2 that are actually going to be produced, which is 0.0617 moles of CO2. Now we want to take moles of CO2 and convert back to our excess reactant, moles of CaCO3. So we want to go from moles of CO2 to moles of CaCO3. So there's 1 mole of CO2 in the equation and 1 mole of CaCO3. And then we want to convert that to grams of CaCO3. So we're going to use 1 mole is equal to the molar mass, which is 100.06 grams of CaCO3. So when you calculate that, you get 6.17 grams. But that's not our answer. 6.17 grams is how much of the CaCO3 was used up in the reaction. To find out how much is left over, you're going to take your original 15 grams, subtract what was used, and that will tell you how much is left over. So we get 8.83 grams of CaCO3 left over. Okay, so example number 2 for 2C says if 15 grams of copper 2 chloride reacts with 20 grams of sodium nitrate, how much NaCl is going to be produced? What is the theoretical yield for sodium chloride? And then we have to also figure out how much excess reactant will be left over. So we're going to start with our 2 calculations, one from calcium 2 chloride to NaCl, and then the other from grams of NaNO3 to moles of NaCl. So start with your 15 grams of calcium chloride. Use the molar mass to convert from grams to moles of calcium chloride. And then the mole ratio to go from moles of calcium chloride to moles of NaCl. Okay. So when you do that, you get 0.223 moles of NaCl. Second calculation is from 20 grams of NaNO3. So we want to go from grams to moles of that. Molar mass is 84.96 grams. And then in the equation we have 2 moles of NaNO3 for every 2 moles of NaCl. So when you do that calculation, you get 0.235 moles of NaCl. So your limiting reactant is going to be the 15 grams of CuCl2 because that produced the lesser amount of product. And now we're going to take that moles of NaCl and convert it to grams to get our theoretical yield. Okay, so we have our 0.223 moles of NaCl, and we just want to use the molar mass of NaCl to get to grams, which is 58.44 grams of NaCl. So that gives us 13.0 grams of NaCl, and that is the theoretical yield. So that answers the first question. The second question is how much excess reactant will be left over. So again, we want to take the moles of NaCl that are going to be produced. And now we want to go from moles of NaCl back to grams of our excess reactant, which was NaNO3, to figure out how much of the NaNO3 is used in the reaction. So we have 2 moles of NaCl for every 2 moles of NaNO3. And then the molar mass, which is 84.96 grams of NaNO3. So that gives us 18.9 grams of NaNO3 that is used up in the reaction. So if we started with 20 grams of NaNO3, do 20, subtract what was used, and that gives us 1.1 grams of NaNO3 left over. Right? So the theoretical yield for NaCl is 13.0 grams, and we have 1.1 grams of NaNO3 left over. So now this is example 1 for 2D percent yield. However, it's going to be using what we just calculated for the theoretical yields of NaCl in the previous problem. So the problem says if 11.3 grams of NaCl are isolated after carrying out the reaction above, calculate the percent yield for NaCl. So if you remember, to calculate percent yield, you do the actual yield over the theoretical yield times 100. So this 11.3 grams of NaCl, that's the actual yield that was found by doing this experiment in the lab. So you're going to do 11.3 grams divided by the 13.0 grams that we calculated as the theoretical yield in the previous problem times 100, and that will give us 86.9% yield. And that is your answer. All right, so example 2 for 2D says you are doing an experiment with the reaction above. You start with 200 grams of C7H6O3 and end up with 231 grams of C9H8O4. What is your percent yield for this reaction? So let's look at what we're given. We're given 200 grams of C7H6O3, and we're also given the actual yield of C9H8O4. So we need to start with the 200 grams of what we're given and calculate the theoretical yield of C9H8O4 so that we can use the actual yield to calculate the percent yield. So we're going to do one calculation from grams of C7H6O3 to grams of C9H8O4, then we'll use that to calculate our percent yield for this experiment. So 200 grams, and we need to convert that to moles using the molar mass, which is 138.04 grams. Now we want to use the mole ratio from what's given to what we're looking for, so that is just 1 to 1. And then we want to convert our product to grams. So our molar mass is 180.05 grams. So when you calculate that, you get 261 grams of C9H8O4. Okay, so the problem is asking us to calculate the percent yield. So 231 grams is our actual yield. 261 grams is our percent yield, or our theoretical yield, and we're going to multiply that by 100 to get our percent yield, which is 88.5%. So that is how to calculate theoretical yield and then percent yield. You have some practice problems in your packet, so go ahead and work on those and let me know if you need help.